We've talked a lot so far about representing, naming, and visualizing chemical substances. In this module, we're going to turn our attention to the question of counting species within a chemical substance, representing what we'll call amount of substance. The unit we typically use to do this is called the mole. We'll talk about the origins of the mole in great detail in this module, and we'll often use a kind of conversion factor. It's not exactly a conversion factor, but we can think of it that way, between mass and moles. In the laboratory world, we measure amounts of chemical substances most commonly using mass and volume. But in our minds, in the mind of a chemist, we don't like thinking about mass. Mass varies across different chemical substances. Instead, what we want to think about are numbers of species, numbers of atoms, numbers of molecules. Chemists love counting. We like thinking about molecules combining, for example, in small whole number ratios, 2 molecules of this and 3 molecules of that in a chemical equation, for example. And so we need a means to go from the macroscopic world of masses and volumes to the submicroscopic world where we love counting molecules, and the mole and molar mass are means to do this. So in this first section, we're going to focus on the first couple of learning objectives here. We're going to talk about the origins of the mole and why Avogadro's number, probably the most famous number in chemistry, has the value that it does. We'll talk about average atomic masses and learn how we'll use those to calculate the mass of a single molecule for a molecular compound, for example, and then what we'll call the molar mass. And then we'll apply molar mass to go from the amount of a substance in moles, the number of molecules essentially in that substance in moles, to the mass, and vice versa. Let's start with a pretty basic question here. How much does a molecule weigh? Well, from the periodic table, we get a sense of how much atoms weigh. The weights of atoms are measured with reference to a standard involving carbon-12, the isotope of carbon with 12 protons and neutrons in the nucleus, 6 protons and 6 neutrons. The atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom, so that carbon-12 weighs 12 atomic mass units. Every other atomic mass on the periodic table is defined relative to carbon-12, and this includes the mass, the average mass of a carbon atom, which is a little bit bigger than 12, since carbon, in its natural form, consists of carbon-12, carbon-13, and carbon-14 isotopes. So all of the masses that you see on the periodic table are averages, average atomic masses, over the various isotopes of that element that we find in nature. One atomic mass unit is a very, very, very tiny mass in grams, 1.661 times 10 to the negative 24 grams. This just reflects the fact that atoms are extremely tiny, of course. And the third bullet point is very important to understand conceptually, that whenever we're looking at a macroscopic sample of any chemical substance, be it an element or a compound, the masses of the atoms that we perceive in this huge, huge collection of atoms or molecules reflects the average across all isotopes. And so we use the average atomic masses on the periodic table to get a sense of the mass we would observe for that atom on the macroscopic scale. This becomes important when we start asking about the mass of a molecule. The mass of a molecule is the sum of the masses of the atoms within that molecule, but the mass we observe on the macroscopic scale, where there is an uncountably, well, not uncountably, but almost unfathomably huge number of molecules in the sample, the mass of each atom reflects the average over all the isotopes. And so when we talk about the formula mass of a substance, this is the mass of a single molecule, where we use as the atomic masses the average atomic mass off of the periodic table. We're going to use the compound benzoic acid throughout this unit to talk about atomic and molecular mass and related quantities. And we're going to start with the formula mass of benzoic acid. It has the chemical formula C7H6O2, And to find the average mass of a molecule of benzoic acid in any macroscopic sample, the formula mass, we're just going to add up the average atomic masses of the 7 carbons, that's here in purple, 6 hydrogens, here in black, and 2 oxygens, here in red, and the total here is 122.123 atomic mass units. You can think of this is about 10 times as heavy as a carbon-12 atom. One thing to point out here is this is still an extremely tiny mass, right? We're taking 1.661 times 10 to the negative 24 grams and multiplying that by 122. That's extremely, extremely light still, right? We're talking about the mass of a single molecule of benzoic acid on average in a macroscopic sample of benzoic acid. Now that we know the mass of a single molecule of benzoic acid, if we know the mass of a macroscopic sample of the compound, we can calculate the number of molecules in the sample. And on the slide here, I use the general term particles, since this would apply whether the substance involved atoms, molecules, ions, etc. And proportional reasoning is involved in this idea. So for example, say we had a sample of benzoic acid that had a mass of 5 grams. How many molecules of benzoic acid are in this sample? Well, we know the mass of a single particle of benzoic acid, a single molecule of benzoic acid. It's 122.123 atomic mass units. And the total number of molecules is just the total mass of this sample, 5 grams, divided by the mass per molecule, right? Since the number of molecules present times the mass per molecule is going to equal the total mass. This equation is just a re-expression of that idea. So we can plug in the numbers given. 5 grams is the total mass of the sample. We know that the mass per molecule is 122.123 atomic mass units, and all we then need to do from here is a unit conversion, either converting the 5 grams into an unfathomably huge number of atomic mass units in terms of mass, or, as I do on the slide here, convert this 122.123 atomic mass units into grams. We do that by multiplying by the conversion factor we saw on the last slide, that an atomic mass unit is equivalent to 1.661 times 10 to the negative 24th grams. This turns out to be a crazy huge number. One thing I will point out is that grams divide out with grams here, and atomic mass units divide out as well, so that all we're left with is a count of the number of molecules in the sample, and this turns out to be absolutely huge, 2.46 times 10 to the 22nd power, literally unfathomably big. Macroscopic samples of compounds contain huge numbers of molecules. Despite those huge numbers, though, we're still really interested in this count, since the way molecules engage with each other on the submicroscopic level is based on their number, not their mass. And so we do need a very large counting unit for molecules. Any macroscopic sample is going to have something like this number or more of molecules in it, right? And so our counting unit needs to be on the order of like 10 to the 20th power, or maybe even bigger, right? To bring counting numbers, the values of these counting quantities, into more human-friendly territory. And this leads into the mole, and it's our motivation for defining the mole. You may know from prior work in chemistry that the mole is a counting unit corresponding to 6.022 times 10 to the 23rd of actually anything: atoms, molecules, photons, Legos, muffins, anything. The mole is a counting unit, like a dozen or a couple, corresponding to a specific number of things, and that number of things is 6.022 times 10 to the 23rd. Why that number, though? What is so special about 6.022 times 10 to the 23rd? That specific number of things leads to the situation described in the first bullet point of this slide, which is highly, highly convenient. That number of things, 6.022 times 10 to the 23rd, leads to a situation where the mass of a set of molecules, 6.022 times 10 to the 23rd molecules, has a mass in grams equal to the mass of a single molecule in atomic mass units. That's worth saying again. The mole is the number of particles in a substance with a mass in grams equal numerically to the mass of a single particle, atom, molecule, etc., of that substance in atomic mass units. This is a highly convenient definition since we already know how to calculate the mass of a mole of any substance from 2 slides ago. We know how to find formula mass using average atomic masses from the periodic table. We did the example of benzoic acid and found that a single molecule has a weight or mass of 122.123 atomic mass units. Immediately, based on this definition of the mole, we can conclude that the mass in grams of a mole of benzoic acid is 122.123 grams. This is the beauty of the mole. We can use formula mass and the mass of a mole, we'll give a name to that in a second, pretty much interchangeably, just by changing the units. 1 mole of benzoic acid has a mass of 122.123 grams, and if we zoom in on a single molecule of benzoic acid, a single molecule has a mass of 122.123 atomic mass units. And the mole is a counting unit. If it helps, think of it like a dozen. A dozen corresponds to 12. A mole corresponds to 6.02 times 10 to the 23rd. Doesn't roll off the tongue quite as easily, but conceptually, it's exactly the same. It's a representation of a count of atoms, molecules, ions, photons, number of reaction occurrences, and a wide variety of other things that you'll encounter in your future studies of chemistry. When the mole refers to a count of material particles or species, atoms, molecules, ions, etc., it gets the kind of formal name amount of substance. And this word amount, when you hear it in chemistry, should trigger the concept of a count. It is the count of particles in that substance. This term amount of substance is the term we use for that. And so what we can do with the mole now is keep track of numbers of particles from macroscopic masses in grams without having to use these astronomically huge numbers like 2.46 times 10 to the 22nd. This is going to be a very nice looking number like 0.1 moles instead of this unfathomably huge number of molecules that's really hard to wrap our minds around. We already touched on this, but 1 mole corresponds to a fixed number of particles, and this number of particles, 6.022 times 10 to the 23rd, you see it in the bottom right of the slide here, is known as Avogadro's number. We can find Avogadro's number knowing the size of an atomic mass unit and the size of a gram, right? Since the mole is defined as the number of particles, that allows us to go from the mass of a single molecule in grams to the mass of a mole in grams in a way, right? And so, for example, to calculate Avogadro's number, we can say, okay, by definition, a mole of benzoic acid weighs 122.123 grams. A single molecule of benzoic acid weighs 122.123 atomic mass units. So when I divide the mass of a mole of particles by the mass of a single particle, the result I get is the number of particles in that mole. And this comes out to 6.022 times 10 to the 23rd for benzoic acid, and indeed for absolutely any substance, right? Because based on the definition of the mole, these two values will change, but they'll change together, right? As the mass of a single molecule gets bigger, for example, the mass of a mole will get bigger, and vice versa. And so Avogadro's number really pops out of this conversion factor between the atomic mass unit and the gram. At the end of the day, Avogadro's number is the same for all substances based on the definition of the mole. You'll sometimes see Avogadro's number written with units of per mole. Sometimes we'll fill in something before that per mole, atoms, molecules, photons, etc. Though we don't have to. We can keep this general. And so you'll see it written as moles to the -1 power, right? That's the same as per mole, or even just with a slash mole, right? Indicating we're dividing by moles. Avogadro's number is anything, in brackets here, per mole. And the count is typically clear from the context. When we start working with atoms, molecules, and ions, and the mole, though, things can get a little confusing because it's possible to have different counts of different types of particles within a substance. If, for example, an ion appears multiple times within a formula, we may have a bigger count of ions within a substance than the count of formula units as a whole. This is why I suggest whenever you're working with mole units, include a chemical formula after the unit mole so that you're clear in your mind about what you're talking about. The count of, right? Moles of what is the question we want to answer with that chemical formula that follows the word mole. So for example, if I just spit out a measurement here, for instance, 3.2 moles. Well, moles of what are we talking about? Atoms, molecules, ions, moles of what exactly? And if I include a chemical formula like C7H6O2, now I know I'm talking about 3.2 moles of C7H6O2 molecules. The count of benzoic acid molecules is 3.2 moles. The counts of the atoms within those molecules are not 3.2. For example, there are 7 times 3.2 moles of carbon atoms in this compound, since each molecule contains 7 carbon atoms. And so another point I'll make here that I often make when the mole is first introduced in my intro chemistry courses is moles are not conserved, right? It's not like the counts of all the atoms within a molecule have to add up to the count of molecules in a sample. In fact, in general, they won't, since a molecule will have multiple copies of most types of atoms, right? The count of oxygen atoms is twice as big as the count of benzoic acid molecules in any sample of benzoic acid. And this is worth keeping in mind, along with this idea of including a chemical formula to clarify in your mind the answer to the question, moles of what? Now, we can infer from the way we've written Avogadro's number here that it's a way to convert from a number of moles to an absolute count of particles, or vice versa. So for example, and we'll do this on the next slide, we already calculated the number of molecules in 5 grams of benzoic acid. If we wanted to express this in moles, the way to do this would be with Avogadro's number. And you may have an intuition for this already. We're going to take this and divide it by the number of particles in a mole to get this number of molecules expressed in units of moles. I've alluded to this already, but the mole is much more convenient to work with and much more human brain friendly than these absolute counts of molecules that are universally astronomically huge. And so we like to express numbers of molecules in units of moles, and Avogadro's number is the key to going between number of molecules in an absolute count sense and number of moles. So for example, we previously calculated that in a 5-gram sample of benzoic acid, there are this many molecules, astronomically huge number. To express this in moles, to express this count in units of moles, what do? Well, we use Avogadro's number and the fact that it has units of per mole, or molecules per mole in this case, right? In 1 mole of benzoic acid, there are this many molecules, and we can see that the molecules units will divide out here, and we're left with 0.0409 moles, a much more human-friendly value, right? This is about 1 over 25. I can get a sense of this, get a feel for this in human-friendly terms. It's a much more human-friendly value than this unfathomably big number. We can also use Avogadro's number to go the other direction. If we know the number of moles of a substance that we're dealing with, we can find the corresponding absolute count of molecules, formula units, ions, atoms, what have you. So for example, we've got 2.5 moles of CaCO3. This refers to the formula unit CaCO3, so 2.5 moles of CaCO3 formula units, right? Visualize that in your mind. That's calcium cations, carbonate anions. We've got 2.5 moles of that formula unit. We know how many formula units there are in a mole of this substance, 6.022 times 10 to the 23rd, as always, right? So we can use proportional reasoning here again and say, okay, Avogadro's number of that formula unit are present in 1 mole. So in 2.5 moles of the substance, I've got 2.5 times 6.022 times 10 to the 23rd divided by 1 mole. Moles divide out, and I'm left with 1.51 times 10 to the 24th formula units. Personally, I'm not fond of asking questions like this, since really you should strive to go in the opposite direction and express things in the human-friendly unit of moles as much as possible, but it highlights the principle that we can use Avogadro's number to go from a number of molecules to a number of moles, or in the other direction, a number of moles back to number of molecules. From the way we define the mole, we know that the mass of a mole in grams is numerically equal to the formula mass of the substance in atomic mass units for a single particle. This means that we can apply what we already know about determining formula mass to determining the molar mass of a substance. Molar mass is the mass in grams of 1 mole of a substance, and so it has units of grams per mole, which you'll see represented this way. And just to highlight this, I wanted to work through a quick example with morphine. Morphine has the formula C17H19NO3. And to find the molar mass of morphine, the mass of a mole in grams, we just apply the exact same approach we would to find the mass of a single molecule in atomic mass units. 17 carbons have a mass that looks like this, 17 times the average atomic mass of carbon. Notice I've made a subtle change of units here, where this mass, this average atomic mass of a single atom of carbon, is the same numerically as the mass of a mole of carbon atoms in grams. So the atomic masses that you see on the periodic table are also molar masses for the atoms of the elements. So 12.011 grams per mole is the molar mass of carbon atoms. Likewise, for hydrogen, we've got 19 of those, 1.008 grams per mole of hydrogen atoms. We've got 1 nitrogen, 14.007 grams per mole, and we've got 3 oxygens at 15.999 grams per mole. And we just add up all of these molar masses to find the mass of 1 mole of morphine. This turns out to be 285.343 grams per mole. But the approach you can see in terms of counting the atoms based on the chemical formula and multiplying by, in this case, the molar mass of that element is exactly the same as what we did previously to determine the formula mass of a single molecule or single formula unit of a chemical substance. And the beauty of molar mass, again, is that we can use it to go from a mass, say we measured in the laboratory, to a number of moles, a count of particles within that substance, or from a count of particles to a mass. It's a conversion factor of sorts in that way, and we'll work with it in the next video to see that in more detail. Some lingering questions here I'll leave you with. The reason Avogadro's number has the value that it does, we saw, is basically based on the definition of the gram, right? What we did was we went from the scale of a single atomic mass unit to the scale of a single gram. The number of particles needed to do that is Avogadro's number. But what if our target mass unit was not a gram? What if it was a pound or even a kilogram? Would the definition of the mole change? And can we even define the mole with respect to mass units other than the gram? The answer is yes. You'll probably never see this unless you're a chemical engineering student, in which case you may. What about substances that we can't weigh? So how do we count molecules if we can't use molar mass, since we can't weigh a substance? For example, substances that are dissolved in solution, we can't weigh directly since they're always bathed in liquid, right? Liquid solutions have solutes that we can't weigh directly. How do we count particles of substances found in solutions, for example, is a lingering question. And then how we actually use moles. And this is something you'll definitely touch on in your introductory chemistry course. How do we use these counts of atoms and molecules to plan and carry out chemical reactions?